Okay. Day 2, part 2, continuing on. So now we're basically ready to start making mods to our post here. So I'll go ahead and pull that up at the same time. Open up our Cincy 5-axis gantry. And if we start from the top, we're going to scroll past kind of the selection variables that are meant to be edited. So with this 5-axis post, there are configuration switches that change the kinematic setup for the machine. But there are also switches that just suit your own personal preference. Factory set program switches and debugging, most of this stuff you're not going to need to mess with. Then we get down to program control, and these are absolutely designed for you to edit and make choices about how you want the code to come out. Stage tool. Remember what I said at the beginning of class about the configuration for the 5-axis post? There are a lot of things for the 4 and 3-axis posts that have been either hooked up to the machine definition or hooked up to the control definition. For the Generic Fanuc 5x mil post, that is pretty much the opposite. Most things are set strictly inside the post and not in those other locations. So stage tool is one of the things where we have that option in the control definition, but nobody's taken the time to go back and hook up the logic inside the post to read it from the control definition. So it's actually configured here. If you want stage tools turned on, you set it to 1. Otherwise, you leave it 0. Program name is a command variable that forces the program name to be converted to uppercase. Do you want it forced to be converted to uppercase, or do you want to allow lowercase and mixed case characters? You can make that decision here. Enable automatic subprogram support. You notice it's turned off. Do not enable. Okay, it's telling you right here, the post has not been configured for subprograms. This is an interesting one because this isn't something that you want to edit, but it's something that you can use to test. So cut flag is similar to cut pause 2 or cut pause, which is a predefined variable, only this one gets explicitly set inside the PSB. So cut pause and cut pause 2 are toolpath flags that get set based on the type of motion you're doing. Cut flag is actually an internal variable that gets assigned by MP, or well, by the PSB really. So what you can do is you can test and see if cut flag equals 1 or 2 or 3 or 4 or 5 or 6 or 7. And based on testing this cut flag, you can know where you're at in the cut. Am I approaching the part? Am I in the lead-in motion? Am I in the middle of the cut? Am I in the lead-out motion? Am I at the very end? Am I retracting or am I at the plunge point? So this is actually the very tall plunge point. This is the very final retract point. This one is the motion kind of before the entry. This one's the entry. This one's the path. This is the exit. This is after the lead out. And then here's the final retract position. Work offset control. Initialize work offset. This makes sure that our first work offset comes out. So if it's 0, we get a G54. This is an important one. Force WCS is set to yes. Force WCS output at every tool change. When they say force WCS, what they're really talking about is force the work offset output. It should be okay, force G54, 55, 56, whatever. Okay. And this is another important one. Use first WCS. Only use the first work offset and ignore all others in the NCI. So when that's set to yes, only the first work offset that is used inside the operation will get used. So this is important because if you don't know this switch is turned on and you go and set your first work offset to 0 and your second one to 1 and your third one to 2 because you're expecting G54, 55, and 56, you'll only get G54 because this is turned on. However, if you're only using a single work offset and you're programming from the center of rotation, or in the case of a gantry, the part doesn't move, then you can leave this set to yes and only use a single work offset. Use gear. Do you want gear codes or not? Does your machine need them? Min-max spindle speed. We set it here. To change these, you can either use the Boolean word for 0, which is no $, or you can set it to 0. So 1 is yes, 0 is no. Or you can type in the no $. Same thing for use gear. 0 would be off, 1 would be yes, but this would be the same as if you just said yes, $, or no $. So those are basically interchangeable. So min-max spindle speed, convert to rapid. Now this one, you'll notice is a predefined variable and it is read from the control definition. So if you want to convert the rapid moves into feed moves, you can turn that on and it will be read from the control definition. Use feed rate. All of the feed rate control is set here in the post. It is not read from the rotary axis properties. So here we've got a choice. How do we want the feed output? 0 is program feed rate. You program F50, you get F50. 1 is inverse feed rate for everything. 2 is inverse feed rate on 5-axis continuous. And 3 is inverse feed rate on motion with rotary. Typically, for a 5-axis gantry like this, we're going to use a setting of 2. Now this will also depend on if we are using tool center point control or not. Tool center point control is dynamic tool length compensation. If we have tool center point control, then the machine itself does all of the feed rate calculations to synchronize the rotary and linear motion. If this is true, we can leave this set to 0, we can output at the program feed rate, and we have to add code to support tool center point control. This post, in its generic form, has no code for tool center point control. It also has some structure for tilted work plane, but needs you to finish setting it up. It's not set up to be used out of the box by default because there are so many different ways to implement those features. It really needs somebody to customize it for your control. Now, if we're using inverse time when we're doing 5-axis continuous motion, we have to choose the inverse feed type. This basically tells us where are we doing the calculations mathematically to come up with our inverse feed value. We'll come back to this. I'm going to go tip to pivot for now. We'll come back and talk about why. There's a switch for inverse feed rate in seconds. Normally, the inverse feed rate value is in minutes. This one, if your machine has it, feed rate in seconds can sometimes give you more range in terms of what those values represent. Radius feed rate. So this is a variable that's available to you to affect primary feed and secondary feed if you are doing degrees per minute output, but it's not hooked up all the way. The user has to add code to support the radius feed rate option for calculating degrees per minute. That gets messy, quite honestly. Trying to use live 5-axis on a machine without at least inverse time is asking for a whole bunch of trouble, honestly, guys. We'll get into that a little bit more this Saturday. So this Saturday, Wing was asking about some 4-axis continuous, how to do some 4-axis like swarf cutting. So we'll take a look at that on this Saturday. We're going to set up a simple example with the 4-axis, and we'll do some vector-based toolpaths and talk about what does it take on a 4-axis machine to make a multi-axis cut. What does it take to do it successfully? Max feed per minute. Max feed per minute, or max metric feed per minute. So we have these options here that we can set the maximum value for our inverse time, etc. We're going to skip over these for now. We're going to come back to them. So when we do these classes, just had a question that came in. When we do these classes, we typically don't do makeups for them. What we do is we record the course, and then we give you access to that course for like 60 days as part of being enrolled in here. We also have a couple of guys. So for Don and Jeremy, you guys are in here because Ron was kind enough to loan me a hasp. And so I said, hey, what can I do to to pay you back for that? And so that's why you guys got invited in. So no, I'd say, catch it, catch the next one, or use your phone. You can always call into the meeting on your phone and watch. I don't know if you can break away for an hour or an hour and a half, but that's always an option to you. I'm trying to to walk the fine balance between, you know, giving you guys access to the course to help Ron out as a favor to him, because he did me a favor, and not having to go through e-apprentice and get you guys actually enrolled in the class, because there's a whole bunch of stuff that has to happen behind the scenes that I don't have access to. So, kind of is what it is, unfortunately. But, you know, if there's other stuff that you want to see, you know, put in a request for the office hours and we can cover some of that stuff at a later time. So we've got, you know, 4 of those office hour sessions coming. So there's plenty of stuff we can cover. So it kind of is what it is, unfortunately. Okay. I'll just say a word about this right now. Primary angle output and secondary angle output. These 2 switches give us the same functionality as if we went in the machine definition manager. And we went to the rotary axis properties and we changed these options here. Okay, so all of these options, sign continuous, sign direction. So what are the outputs? What's the difference between these 3? Sign continuous. The axis can rotate plus or minus, and it's allowed to wind up. So it's allowed to go beyond 360 plus or minus. If we put in plus 1080 degrees, it's going to do 3 revolutions. If we go minus 720, it's going to go 2 revolutions. Signed direction, absolute angle, is plus or minus 360 degrees. So this option gives us 720 degrees of total travel before the axis resets. And if we go beyond that, basically it just goes back to 0, really. And it depends. Some machines will just allow you to wrap over, and some won't. Shortest direction, absolute angle 0 to 360, always keeps the angle positive between 0 and 360. And if we go to 361, it'll just be output as 1 degree. If we go to minus 360, it'll go to, actually this won't even go minus. So this always limits it between positive 0 to 360. Those choices are not made in the machine definition for this post. Those choices are made here. But here's my word of warning. Don't set these till the very end. Always leave these 0 when you are testing the post, because you want to see what the raw output is before we apply the logic that resets whatever the value is. Okay? So always leave these 0 until you've got the vector directions and the rotary axis stuff set up. Always leave them 0 until you've set your travel limits. Trust me, do all that configuration first before you touch these. Then, once we get through all those regular decisions, right, all these regular variables that we set, these ones, by the way, are just initializations, so we don't need to worry about changing these at all. General output settings, tool info. Output tool table information. It's a question. 0 is off. Do not output any comment, any tool comments, or any tool table. 1, tool comments only. 2, tool table in header with no tool comments at the tool change. 3, which is what it's currently set to, tool table in header with tool comments at the tool change. So you can make your choice here. Rotary settings. Here's where we actually get down to setting up the machine. Assign axis address. Primary axis, secondary axis, dummy axis. We only need to worry about setting these 2. If the machine is C on A, we make it C on A. and we typically set the dummy to B. If it's C on B, we set it that way. If the primary is A, we set it to A, and the secondary C, we set it that way. So, however your machine is configured, we're going to set the primary and secondary. And again, we can wait on setting those kind of till the end as well. M-type. We're not even going to worry about these because these are used for nutating. Oh, tool plane mapped to top angle position strings. These are actually used for two things. They're used for the nutator, and here's something that's kind of funky. This post has logic for tilted work plane output. It has some architecture that's put in. That architecture uses the nutating variables in the background, and it just does that for economy. So instead of creating this whole other set of values separate for the tilted work plane, they just reused some internal logic. So some of the nutating stuff actually controls tilted work plane. It's kind of funny. M-type. We're setting up a head-head machine, so we need to change that to 2. You can see the different values here. Head is secondary. This is only used with M-type 1 and 4 to control whether the head is on the secondary or is on the primary. These 4 variables right here are what configure the rotary axes, both the direction and the positive rotation is all done with these 4 variables. When we look in the 5-axis generic post PDF file, you can see it talks about the post type variable. So type table is type 0, tilt head table is type 1, and head is type 2. They have this very confusing set of slides that we've already been through about setting, how to figure out which one's the primary and which one's the secondary. When it comes down to it, for all 4 of these variables, and the variables I'm talking about are rot axis 1, rot dir 1, so there's rotary axis and rotary direction, and then rotary axis 2 and rot dir 2 can only have 6 possible choices. Sorry, this keeps jumping around here. So when we look at the post, all 4 of these variables are either going to be vec x, vec y, or vec z. So this could be vec x, it can be vec y, or it can be vec z. Or it can be negative vec x, negative vec y, or negative vec z. Those are the only options for all 4 of these variables. The most confusing thing about trying to figure out this whole setup for the rotary axis and rotary direction is knowing that we define a rotary axis using 2 vectors that are perpendicular to the axis. That's it. So here, for example, rotation axis normal. If we're rotating about z, what rotary address letter typically rotates about z in a standard configuration? Zeke's got it. C. So you can see that that's the rotation axis normal. That means that if our rotary is a C-axis, it has to be defined in terms of X and Y. So if our primary is Z, we will never see Z in the name here. It's either going to be X or it's going to be Y. Okay, so when we started this, we had vec Y as the 0 and vec X as the direction for the primary. This is the primary. If we're defining the primary, it's these two variables. And if we're defining the primary as a Z-axis rotary, as a C, it has to be defined in terms of X and Y. So this is either going to be vec X or vec Y, or negative vec X or negative vec Y. Those are the only 4 choices we have for each one of these. And they can't be set the same. They have to be set to be using 2 perpendicular. Okay, so if this one, remember we started with this one as vec Y. So if this one is vec Y, this other one has to be either positive vec X or negative vec X. Oh, yeah, no, C on a gantry is typically primary. So remember, we're defining a gantry. So what this is saying, vec Y rotating towards vec X. If we look here, you can see this is vec Y rotating towards vec X. And what we mean is this positive vector here. And if we say that this is the positive vector, the 0 location, what we're saying is that our tool spindle is, the tool tip is pointing towards 0. And the holder is pointing towards positive vec Y. So this would be the 0 location rotating towards X plus positive. Now we've just changed M type. So I'm going to hit save. And before we get into setting the primary and secondary, I'm going to do a couple of things. Down here for the tool length variables, okay, most of the time these tool length variables are only used for head-head. So we've got a couple of choices here. Use tool length. Use tool length, read from tool overall length. 0 equals use the tool length variable. 1, use the overall length for the tool in Mastercam. 2, prompt the user to enter the gauge length of the tool during the time of posting. Those are the choices we get. I'm going to go 2 for the prompt. Because I'm using the prompt, the tool length variable is ignored. So there's use underscore T length, and then there's tool length set to 0. Shift Z pivot. Shift Z by the tool length. Head program to pivot. So typically with a 5-axis machine that is a gantry, our XYZ location values do not represent the tip of the tool. They represent the pivot point of the machine. It's very important to understand that. So 0, we're going to output the pivot point of the machine, not the tool tip. And this has to do with the controls for these older machines not being able to dynamically calculate tool length compensation. G43 only works along the Z-axis of the machine, typically, if we specify Z. So on a Fanuc, you can only compensate the tool length in the Z-axis direction. As soon as we start rotating the rotary axes on that head, then all bets are off. And so as a result, they had to be able to come up with a method for programming these types of machines, back 20, 30 years ago. Literally, this is kind of like, this post came out right around the time they first released version 9, and I want to say that was 98 or 99. Might have been 99. I think X came out in like 2001 or 2002. So this post's been around a very long time. And, people were successfully driving these 5-axis machines before we had any of these fancy programming strategies like dynamic work offset and tool center point control. Before that, you had to make the post do all the calculations. Add tool length after intersecting limit. Always on if limit from stock. Set that one for now. For using right angle heads, that's what this applies to down here, for controlling the offset. So tool length, we're going to prompt for the tool length, and we're going to output the pivot point of the machine. I'm going to save it now. And I changed the type of machine and left the vector directions the same. So now I'm going to post it out. Enter the pivot length for tool 256. Well, let's say that we measured and it was 14.6252. So I'm going to enter that distance, and we'll repost the machine. And here's what's happening. We got C180, A negative 90. Now, either one of two things has to happen to get C to 0 with this current configuration. Assuming, again, that we've still got an AC machine. We go back into these vector directions, and 0 is vec Y. To rotate 180 for my 0 point, I just put a negative sign in front. Now, I know for my secondary, I want an A-axis. If I want an A-axis that rotates about X, I can't have X in here. So we're going to make that negative Z for the 0 direction for the vector, and rotating towards vec Y is positive. So I'll make those changes, save it, and repost. Enter the same pivot length. And now I get a C0, A90, A negative 90. Okay, because I've started my toolpath here. At the bottom, right? We started down here, and we're running this way. Well, let's say that I go out to the machine, I throw it up there, and when it reads the code, my spindle's actually sticking out the other way. This isn't negative 90, it's positive 90. To reverse the direction, we just reverse the sign. So I'm going to change the sign for direction 2 and repost. Give it the same value. Now, if I don't want to have to keep typing in that number, I can do this. I can go edit the tool. And I can put in the pivot length as the overall length of my tool. Now, what's the disadvantage of doing it this way? This is the disadvantage. Okay? It changes your graphics, and so it doesn't let you use, you know, the real tool length that you're sticking out and the holder and the whole 9 yards, which, you know, kind of sucks, to be honest. So, yeah, there's, you can either prompt or come up with another method for passing the data to the tool length, because right now this is, I mean, it works, but it's kind of not ideal, right? Now, in order for us to take advantage of that, we'd have to go to the tool length and say, use tool length, read from Mastercam overall length. So I'll change that to 1 and save it. Now if we look, post it out. Now we're getting C0A90. Now, remember that this is where we started. So here, the tool's starting at the bottom of the part and cutting around that way. And let's say that we went out to the machine and this cut opposite. We wanted to cut this way. We wanted to cut counterclockwise, but the C-axis motion, even though let's post it out again. So even though we started at 0, if we look at the C is going positive. And positive in Mastercam is counterclockwise. But on the machine, it's actually going the opposite way. It's going clockwise. Well, we want to be able to chain it the direction we're going, and we want the machine motion to follow. That means we need to reverse the rotation of the primary. So we go back in there, we go back to the primary, and we reverse it. So we post it out again. And now, in order for it to cut counterclockwise, like we saw, we're now getting negative motion, which is what we want. So, if we know this direction cutting is negative, and we want to make the tool cut positive, then we have to change how we have selected the geometry. So if we go back into the geometry for this tool path, we can see that this is our chaining direction. So if I reverse that chain, and we regen, I'm going to get rid of those lines because we don't really need them. Here's our path. Post it and overwrite. Now we're getting positive rotation because the tool is traveling the opposite way. So what are the easiest things to remember about this? When you're defining your primary and your secondary, number one is that whatever your actual rotary axis is aligned to in terms of the linear axis on your machine, you will not see that axis in the zero or the direction. These two vectors are always perpendicular to the actual axis of rotation. So if it's a z-axis, you're going to use x or y for both of these. If it is an a-axis, you're going to use z and y. To make this thing a b-axis instead of an a-axis, we only have to change one character here. So we have to change that from a y to an x. This now rotates about y. If we change it to a y here, it rotates about x. It's really just that simple. And then the only other thing that we may need to modify is rotary direction 2. Okay, so if you want to change the sign of the direction, you either remove the negative sign or you add the negative sign. That's it. Literally, these 4 variables right here control both of your rotary axes. It's literally that easy. So, once we get those set, now we also have to look at this too. With our machine, let's set it up for B. Okay? In order to set this up for B, this is my entry. So Jeremy's saying, and vec y rotates around x. Vec z and vec y. You have to have the two perpendicular vectors. So this is the 0 point, which means my tool axis vector is pointing straight down, which is true, right? So at A0, my tool's pointing straight down. Which way does it rotate to be positive? This says if we rotate towards vec y, that is positive rotation, or negative vec y, that's positive rotation. Or if we say it rotates towards positive vec y, that's positive rotation. So this literally controls the direction, and this one controls the 0. So again, let's set this up for a B-axis. A C on B gantry means that we would want the start of our arc to either be at positive X or negative X. To do that, we need to rotate the geometry. So let's make sure, yeah, we're in the top plane. So go to transform, rotate, move it 90 degrees. We regen. Okay, so this means that if I've got a C-axis on B and my tool is vertical, I just want to be able to rotate it over to the left, move my machine over, drop down, and approach this vector. So if I'm rotating for my secondary about B, which is the Y, that means I can't have Y in either of these here. So this has got to be vec X. And it's either positive or negative. We won't know till we try it. So for the C axis, I try to make the directions match. So for C, we would want to make this, the 0 is going to be X. And the direction is going to be Y, and it's either going to be positive or negative. So we'll make this positive vec X, positive vec Y. So again, this is still rotating about Z, because Z is not in here. And this one's rotating about Y, because Y is not in here. And we know we're going vex Z. So I'm going to save it. We're going to look at the input here. That looks good. And we'll post it out. Okay, so where are we starting? Starting at C0A90. And we need to look on our machine and see, if my tool starts on this side, my tool starts on that side facing that way, is that negative or positive? I don't know. I got to go to my machine and check. But right now, my post is saying that's negative. If it's really positive on the machine, then I got to reverse this direction. So I reverse the direction here by changing the sign, and I repost. Now it's positive. I look at my rotation. I back plot it. Okay? It's going clockwise. I look at my code. Clockwise, according to the post, is negative. I got to go to the machine. I got to figure out if it's positive or negative. If it's negative, I'm good to go. If it's positive, what do I do? If I need to change the sign here for my primary, primary is controlled by what variables? Primary is rot axis 1, rot dir 1. The direction, to change it, I change the sign. So I change it to minus vec y instead of positive vec y, and we repost. Now it goes from negative to positive. But again, I have to make sure that clockwise motion for C on my machine really is positive. Okay, so this is clockwise motion. I'm getting positive C-axis rotation. Now, if this really is positive, but I wanted to cut negative, my post is set up right. I just need to, again, change the geometry. So if I reverse my chain and I regen and I post, or backplot, now you can see I'm going counterclockwise and I should be getting negative motion. So, if I look at my code, oh, did I close it? I closed it. So, if I look at my code, and I've got a positive 90, and I'm starting on this side, and I'm cutting negative by going counterclockwise, then life is good for this test. Still got more tests to do, but I think I'm doing pretty good. Now, if I got C90 or C negative 90, that means that my starting point in Mastercam relative to my 0 position in the post is different. So if I take this and I rotate it 180 degrees and I repost it, what do you think I'm going to get? 180, right? I should, if the post is set up right. Ta-da! Okay, and if I rotate it only 90, then I should get 90 in my output. Which I do. So I'm getting C negative 90. So basically, in order for my tool to start here at the backside in Y on a B-axis machine, because that's how we've set it up, right? We've set this up to rotate about Y as a B-axis. In order to get my tool aligned this way, I actually have to rotate the C-axis platter on the machine. So let's rotate one more time. Okay, counterclockwise rotation should be negative C, and this should be A90. Okay, A90, C0, we're getting negative rotation. If I then go in to the machine simulation, remember we are using a C on B. There is some options in here to force it to use different choices on the solution. So, oh, look at this. This is cool. Between 0 and 360. I like that. Okay, so here's the x-axis. I look at my C angles, and I'm getting C of 0, and I'm getting B of minus 90. If I go back and I look in my post, the one thing I didn't change here, we did set this back up for B. So I'd want to change that back. Go back into Mastercam, repost. Okay, C0, B90, and we're spinning C negative. If we look at machine simulation, yep, let me reload this. Takes a second. Okay, so in the machine config, if I go back to post settings and say other solution here, I think that's what we have to do to it. Still giving me negative. Actually, there may be another control that controls in the simulation positive, negative. So I'd have to look at that. But if we start running it, it's actually going positive here. Open the machine tab. Which machine tab, Jeremy? Okay. The pencil. Yep. Okay, let me reset. View. Yeah, it's not letting me go in. There it is. Okay. So now, if I change that to 1 instead of -1, save machine. Oh, come on. Gotta close and open it. Okay. All right. So yeah. So it is possible to reverse those directions and build a machine that mimics the rotary directions of your machine in the real world. Yeah. So that one. Do it or not. Yeah, now we're at B positive 90. And C0. It's still running positive, but we could also reverse the direction of the C-axis. So it's definitely possible to set this up so that the rotary directions in machine simulation match the rotary directions on your real machine. But the real key is that you've got to go look at your real machine in the real world and figure out how it really rotates. Which way is positive, which way is negative, and do some testing. And then first make your post match, and then set up machine simulation so it also matches. So awesome. Thanks for the tips there, Jeremy. It's been a while since I've used the new mock sim. It used to be a little less cluttered in my opinion, but that's okay. You know, they at least they give us the tool. So that's pretty sweet. All right. We are coming up on the end of class. Go ahead and shut down Machine Sim. Does anybody have any questions about the stuff that we've covered so far? I know it's kind of a lot to throw at you, being the second day and all that, but we're going to go through and tweak this a little bit more next Tuesday. And yeah, that's fine. Sure, that works, Chairman. So yeah, we'll be going and tweaking this a little bit more on Tuesday. Wednesday, or not Wednesday, but next Thursday, we're going to start configuring a Trunnion style machine. So really, there's not that much stuff not that many settings that it takes to configure a 5-axis post. You have to set the address strings. You have to set M type, and if it happens to be 1 or 4, you have to set head to secondary. You have to set the rotary axis and rotary axis direction variables. Set the nutating to match if you're doing the tilted work plane. Got a question about tool center point control and dynamic work offset. We'll probably get into doing a little bit of tool center point control. There's quite a bit that has to happen to implement TCP and dynamic work offset. What I will mainly focus on is actually doing the tilted work plane because G68.2 cycle 800, if you're doing Siemens, Traori, no, that's not what we're talking about. But yeah, so I definitely have scheduled tilted work plane. We may try to look at some TCP stuff. But honestly, that's a much more advanced function, and I want to make sure that everybody understands the basic math that goes into calculating angles. So one of the things that we'll do before, so basically TCP is probably the last thing that we'll get to at the end of class. Definitely more concerned with understanding the fundamentals and understanding how and where to make edits to the post. Those two things are really critical. So we'll be going through that stuff. If you're using a head or head table, then you need to worry about the tool length variables. If you're using a table, then you don't. Then there are some variables that have to do with offset of the rotary axis center lines. There's some options for breaking up the rotation and fanning. That's what the break move head stuff does. Top type deals with tilted work plane. Then we get into rotary axis limits. So this has to do with some of the retract and clearance stuff. This stuff's all for controlling the rotary axis rotation limits. And that's pretty much it for doing a basic configuration using the generic Fanuc 5x mil post. It's kind of like right here. Everything for these 5-axis rotary settings from line 354 down to line 561. Those are all the settings that do the basic configuration for the 5-axis. Now, of course, there's a ton of other stuff that we need to know. You know, how to I've got a question about inverse time. Right now, no, because all we're getting is the same feed rate. we would have to go and look at oh, you know what? It is correct. And the reason it's correct is due to the distance between each vector being constant and the distance from center being constant. Now, it's not 63 minutes. So that's the thing. Whenever you look at inverse time, the value for inverse time is not a feed rate in inches per minute. It is the inverse of, it is basically this divided into 60 seconds. You'd have to look at the formula for calculating inverse time. No, it will not take 63.65 minutes to make that move. No, that's only if it was this changes everything. Yeah, it's not going to take 63 minutes to do that at all. There's some thread in here where they do a pretty good job of explaining it. Yeah, it's basically the feed rate divided by the square root of the delta distance. It's it's definitely you can never look at these moves and see a one-to-one, because what you'll find is that really the shorter the distance between the moves, kind of the higher the feed rate value, which is the opposite of intuitive, right? It's not intuitive at all. If we go back to cut pattern, cut tolerance, 0.25. Oh, come on. Maximum step, 0.5. So if we look at this with a much looser tolerance, oh, that's still even. Let's do this. It is barking at me. Okay, so if we have a path with a lot less vectors, okay, the distance between them increased and the feed rate decreased. Because again, it's the inverse. It's such a weird concept. Yeah, it is the inverse. So, here, the distance between our tool axis vectors is pretty minuscule. And the thing that's going to have the biggest effect, honestly, is the inverse feed rate type of where we are taking the calculation from. So you look at this one here, the distance between each move is really minuscule, right? It's very, very tiny. But it's not going to take 318 minutes to move in between each one of these. What we're saying is move between each one of these vectors at the linear feed rate of 6.4. But now put that through this equation that takes into account the total distance that that tool is moving and the rotary axes as well. So, you know, the post knows where the tip of the tool is versus the center of rotation because of the way that we've set this up. So it takes that into account. If I change this to 100 inches a minute, you can see that that value goes way up. So again, it's the inverse of the amount of 3D difference. What you're seeing is an inverse time value. Don't think of it as a feed rate. Think of it as the inverse of the amount of time it takes to complete the move. And if we go here, here you can see because of the real looseness that I gave it, it's just freaking out. Let's do this. This will be fun. Oh, you know what I need to do? Bump that up. Yeah, you can see this one's kind of doing some funky things. So that's a lot of vectors. Told it to oscillate. So here you can see it's kind of some kind of funky stuff going on. And here there's a slight variation because the amount of distance between each of those moves is still pretty minuscule. All right, we're going to go ahead and wrap up class for tonight.